So in differential equations class, one of the first types of equations we learn how to solve is this first order linear or ordinary differential equation. So let's see, that's a lot of words. So we have first order, we have linear, and then we have ordinary differential equation. So what do all of these things mean? So let's start from the top. So first order, this means that the highest derivative that we need to deal with is the first derivative. So we have y here, right? So y is just the variable, and then its first derivative is y prime. And so we see our equation only deals with y prime. We have x, and then we have y. And so just to give you a picture of how this works, if we have x and a y graph here, what this equation is telling us is it's telling us that if we're at any point in the graph, it's telling us how fast y is changing with respect to x. So we can imagine it as like the slope at that curve, but it's not a nice form. It's this sort of beastly equation that we can't really work with right away. So we could, if we knew what y was and we knew what x was, then we could plug in the values of x and y and isolate y prime and find out its exact value. So, but the thing is, we don't always know exactly what y will be and exactly what x will be. So you could kind of imagine if we drew a little grid over here, that at each point in the grid, we could substitute in y and we could substitute in x, and we'd find that what y prime is. So let's say up here it points up, and then maybe it points more straight over here, and then oh my gosh, on this side now it's pointing down, and it's pointing down still, and then this one maybe pointing a little straight. This is just sort of a imaginary field, and maybe it points like this, right? So this is sort of called we could call it a slope field, or you could say a vector field, although vector field is usually reserved for other things. Right now we are only concerned about how y changes with respect to x. So for example, like we can't go backwards here, so we're only like thinking about x going in some direction, and then how is y changing? Is y going up or down? Because this is a ordinary differential equation. So we'll skip linear for now, but we're going to go to ordinary, and ordinary means that we have only two variables that are directly connected here. So y and x, we have these two axes, and they're going to be directly connected. The only thing we have to deal with is we have y and x, and then we have the change in y with respect to x. So this is y prime. That's just another way to write it. It's also sometimes written as y with a dot on top. Usually that's in physics equations, right? You have y dot, and then you might have like y dot dot, or y dot dot dot. They go absolutely crazy with their dots. But we're just going to write it as y prime to represent the derivative. And so this ordinary is pretty important, because I'll just give you an example of a not ordinary differential equation. Is like, let's say we have like an ecosystem, and we have a bunch of different animals in an ecosystem. Well, like if we have, I don't know, a fox and rabbits and grass, right? Those fox and rabbits and grass, they all depend on one another, right? The fox is going to eat the rabbit's going to eat the grass. But then like the grass then sort of depends on the foxes, because the foxes are eating the rabbits, which are eating the grass. So that's going to be a kind of complicated system that is, let's just say it's extraordinary, right? It's not going to fit under the category of an ordinary differential equation. And that's important, because when it comes to actually solving these things, it's helpful to have something that is only two variables and how they relate to each other. So and then the differential equation, this part just means that it's a equation that relates not only y and x, but also how y is changing with respect to x. And differential equations it's a much more general term. So now let's get to this linear part. What does linear mean? Well, linear, so first of all, I'll just get this out of the way. Linear does not mean that p of x and g of x need to be linear. P of x and g of x, these can be whatever they want. You could have cosine of x, you could have e to the power of x, you could have 1 over x. All these things are not linear. What linear means is we're only talking about the terms that deal with y. So we are talking about linear in y. All of the y's are only are only y's and multiplied by something that is not y. So we have y prime, in this case it's not multiplied by anything, and then we have y, which is multiplied by p to the x. The key is that this p to the x, or p of x, does not depend on y. So basically we have y times something, and if we change our y, these, like p of x and g of x, they're not changing if we keep x the same. See how they're basically, these are functions only of x. So if we keep x the same and we change y, the only thing that's changing is this y right here, and then this might change as well. But that's why it's called linear, because this, like, so a not linear, here's something not linear, is if we had y squared, or we had, even worse, the derivative of y squared, or we had, like, I don't know, cosine of y, right? These are all not linear things in y. So for to be linear, we need to have y, basically the only term the only y terms are something that's not y multiplied by just y, or just y prime, or just some derivative of y. And because it's first order, we only have y and y prime. So let's get down to actually solving this thing, and today we'll be talking about my favorite method to solve it, and it's sort of the simplest method, and probably it's the one that works. It's very trusty, right? There are very few times when you have to resort to a different method, and it is called integrating factor. So that's kind of complicated, right? We have integrating factor. We know that integrals are complicated. We don't like integrals. So why would we like integrating factor? And it does involve a couple integrals, but that's okay. They're not hard integrals. We will be able to solve them. It's not some crazy nasty thing that we need to do some massive substitution or something like that. Just bear with me here. So integrating factor, the idea comes from the fact of the product rule. So if you remember back from calculus 1 and AB, the first time you learn about the derivative, one of the things you learn about is the product rule. So this deals with when we have a derivative of a product. Wow, who could have guessed? So if we have f of x times g of x, this derivative is going to be f prime of x times g of x plus f of x times g prime of x. So the idea is that we do the derivative of one and keep the other the same, and then we take the derivative of the other and then keep the first one the same. So then we add them together, right? That's the product rule. Good trusty product rule makes derivatives super easy, and yeah, so we're going to sort of do the opposite of that. And what we want is we have y prime plus p of x times y, and we want to get that into a form that looks like y times something, the derivative of that, equals something else. So we want to sort of condense these two expressions into one expression, and we're going to use some tricks to do that, to figure out what goes in this blank space. And yeah, so let's see. Let's just call it f for now. Now, if we did our product rule of this, then we would have, let's do the product rule. We have y prime times f plus f prime times y. So that's not super helpful. It's actually not really helpful at all. And so we have one more thing that we need to keep track of to make this actually possible. Because first of all, like, okay, well, like, y prime is just by itself. How are we going to have f here? And okay, sure, f prime, we could say, oh well, yeah, that looks like it goes in the spot where p of x goes. But you know, we still have this big problem over here. Y prime has nothing multiplied, like, it's not being multiplied by anything. So how are we going to deal with that? And the last trick comes from the fact we're going to talk about our good old exponential function. And so it's too dark of a color. Let's see, we can use this color. So the exponential function, it's kind of cool because if you take its derivative, it's the same function. It keeps that. And if you have some like, let's say you have e to the ax, its derivative is a e to the ax, so we sort of bring down the a here. And in general, if we have e to the some function, then its derivative is the derivative of whatever that is times the original. So in integrating factor method, we use this fact to basically come up with some exponential function and multiply through all of the terms in our equation. And here we have equals g of x multiply, and we were going to multiply basically every term in our equation, because it needs to stay equal, by the same thing, by the same exponential function. And then now it's going to magically fix our problem of this derivative. So what we want, like let's say we have some, we can just call it f of x. Let's say we have some e to the f of x, and we multiply all of the terms. Like let's say we have term 1, term 2, term 3. We want to multiply them all by this e to the f of x. So let's just do it. So we have y prime times e to the f of x plus p of x times e to the f of x times y. So that's the second one. And then the third one is e to the f of x times g of x. So we have, this is still equal. We multiplied this by each term in our equation. But now what, right? Like, what are we supposed to do now? So the other thing that we know is this fact. We want this to be the same as the derivative of y times e to the f of x. And first of all, we know this because, like here, right, we know that if we take this derivative without knowing what f is, we're going to have y prime times f. And so in this version right here, we have y prime times this e to the f of x. So we know f needs to, like, whatever. I'm sorry I used the same letter, but basically this needs to be here, and so therefore this needs to be here. And so now if we take its derivative, let's just, because we don't know what this exponential is yet, but we're going to figure it out. But first we kind of just have to pretend that we know what it is. And so we have, let's see, we have y prime times e to the f of x, right? We take the derivative of y, keep this one the same, and now we're going to keep y the same, and now take the derivative of this. So now we have f prime of x times e to the f of x. So remember, our rule up here is that we take the derivative of e to the f of x. That's the same as the derivative of whatever the exponential term is, and then the e to the f of x. And then this is all equal to this over here. So we have e to the f of x. Yes, of course, this side didn't change, right? Okay, so now we have this new form, and this is looking, these two right here. This is version 1, this is version 2. They're looking pretty close. So basically, we need to figure out what f of x needs to be, such that these two, we want them to be exactly the same, because that means that this is exactly the same as this. So remember, like this left-hand side here came from this derivative expression. So we're trying to figure out what f of x is, such that it actually works in a way, because of course if it's not equal anymore, then that's a problem. So let's see what's different. So on the top we have y prime times e to the f of x, y prime times e to the f of x on the bottom. That's the same. Okay, let's go to the next term. So here we have p of x. So that's from our original problem, p of x. Then we have e to the power of f of x, like we multiplied through by, times y. And now over on the bottom we have, let's just put y over here just to make it easier. So we have f prime of x, which is different, times e to the f of x, which is the same, times y, which is the same. And then of course this side right here is the same with both e to the f of x times g of x, and then on the bottom e to the f of x times g of x. So the only thing that's different is that in the original we had p of x, and in the other one we had f prime of x. And so the idea of integrating factors say, okay, well, we need these to be equal, because we haven't said what f is yet, but this might give us a way to figure it out. because we know that for it to actually work in our equation, we need f prime of x to be equal to p of x. So this is a derivative. If we want to find out what f of x is, let's just do the antiderivative. Let's cancel out this derivative and then take the antiderivative of this left side. So we know that the derivative of, or the antiderivative of the derivative of something, well, that's just the original. That's just f of x. And now on this side, we're just going to say it's the antiderivative of p to the x. Well, that's f of x. I mean, this, we can't really write it in a better way for now. But, I mean, that is exactly what, I mean, that's, we now know what f of x is. It's just the antiderivative of p to the x dx. So let's try to replace f of x with this expression. So let's see, I guess we need to make some more room over here. So what we had before is, just to recap, we have this expression over here. And the idea is that we've multiplied through our equation by this term e to the f of x. Right? We've multiplied through every single term. And because we've applied it to every term in the equation, even the right-hand side, it's still equal. The equation still works. And the idea is we're trying to use this to condense two terms into one term. We want it to just be equal to the derivative of y times e to the f of x. This is going to make our equation easier, way easier to solve. But they need to still be equal, and so when we expanded this derivative expression, we found that the only real difference was that f prime of x was in place of p of x. So we set them equal to each other. P of x is f prime of x. Then to find f of x, the original, we need to take the antiderivative of both sides, right? We had the derivative of a function. To find the original, we do the antiderivative. And so now we found that f of x is the antiderivative of p of x dx. So let's to make our life easier, so I don't have to write e to the power of something a million times, let's say this new function mu, and this is what we use in class as well. So let's say mu of x is equal to e to the power of this f of x. So it's the antiderivative of p to the x dx. So this is our sort of shortcut here. And let's write our equation one more time. So we have y prime times mu of x plus, and now we have p of x times mu of x times y is equal to mu of x times g of x. So this is like, whoa, this looks way more complicated than our original, right? But just wait, remember we have this trick up our sleeves that we just proved works. It makes the same expression in the end. And so using our new trick, we take these two expressions. This is two expressions, and we represent it with the product rule. So this is actually going to be the same as the derivative with respect to x of y times mu of x. And just remember that the reason for this is because, so in the product rule we take the derivative of y, and now we keep mu of x the same. Now we keep y the same, and we take the derivative of mu of x. But the derivative of mu of x is, since it's an exponential term, it's itself multiplied by the derivative of the exponential. And the derivative of the antiderivative of p of x, that's just p of x again. And so see how all of these terms are sort of generated by this one derivative expression. And because of that, now we can say that this is equal to the right-hand side, which is unchanged, mu of x times g of x. And to finally solve this equation, we can see how we have this derivative here. We can just take the antiderivative of both sides. Why not? We have a derivative here. We can undo it by taking the antiderivative. So we have y times mu of x. That's just the original inside the derivative is equal to the antiderivative of mu of x times g of x dx. And now to finally isolate y, we can get our final expression. We can write it in a new color here. It's nice blue. We can say y is equal to, we can divide by mu of x, and now we have the antiderivative of mu of x times g of x dx. And we finally separated y. Y is by itself finally Uh, and this now this whole side only depends on x. So this is only dependent on x. And so what this means is that in our original graph over here, remember how we didn't really know what y was going to be if we knew x? Well, guess what? Now we do. Now we have this other equation that tells us if we know what x is and we can do this integral, we know what y is going to be. And so what this relates to is this is one of the paths that you can take through this slope field. And this is called a solution. So this we have the slope field, and one of the paths through that slope field is a solution. And now you might be thinking like, wait a minute. We have this one equation, but through the slope field, I mean, we could take all sorts of different paths. We could go this way, we could go this way, we could go this way. And so here's where that comes into play, because this equation still works. So you might have noticed that you might be thinking one thing. You're like, wait. We forgot the plus c when we did the integral. And that's why I say you're exactly right. If we want to turn this into like an actual answer, let's say we had mu of x and we had g of x, we wanted to turn it into an actual answer, well, we need to add the plus c on the end of the integral. So let's say we can turn this expression into this antiderivative plus c. So now it's sort of like an actual integral. And if we really want to be fancy, let's say we want it to be exact. To be exact, first we would, let's erase these x's, and instead we can, let's be like exact here. So we have mu of s and g of s ds. And the integral, now we're going to add bounds to make it something we can actually evaluate, from 0 to x. And now we have the plus c. And this is all sort of together. And so hopefully that wasn't too confusing, that transformation. All we did was we changed the integration variable from x to s, so that way we can use x as a bound, which it should be. And then we add this plus c at the end. So now this is sort of a more rigorous expression. And the more you change c, that's going to change your starting point, which is going to change the path you take. So this c can be anything, and that anything is going to give us a different solution through our slope field. So in theory, there are an infinite number of solutions, and each one corresponds to this c variable. So let's do an example of this. Let's see. Also, if we wanted to write it one last time, it's important to note that this c is it's not just a constant term, it's also like this 1 over mu of x is going to distribute into the c term. So that's important to know. It's not like, oh, we have one solution and we're just shifting it up. Like that wouldn't necessarily be the case. Really what's happening is we have like this c term, if we distribute it out, it's actually c times 1 over mu of x. And so because mu of x is not just a line, right, this is going to be more complicated. And so what it ends up being is, like, let's say we increase c, now our solution might be a little bit different, or it might be a little bit different if we shift it down. But the point is it's going to reflect a different solution in our slope field. So let's get a little space here. And let's get a practice problem. So to get a practice problem, we can say, I guess I'll just make one up, right? So let's say we have y prime. Let's do an easy one. Let's just say it's plus 3y, and then this is going to be equal to, I don't know, we can say it's equal to x squared. Give a little spice to this. So let's see. This, if we wanted to put it in the original form. So I'll just remind you, the original form was y prime plus p of x y is equal to g of x. So if we wanted to sort of plug these in, we could say that p of x, well, that's just equal to 3, right? I know it doesn't depend on x, but this will be an easier example. We can do a harder one in a second. And then g of x, well, g of x is just going to be x squared. So we can say g of x is x squared. Now we have to find the actual integrating factor. So remember, we used this mu of x function a lot. And so we defined it as e to the power of the antiderivative of p of x. And so that looks kind of complicated, but now if you see that usually p of x isn't that hard originally, we can just say this is the antiderivative of 3, which is equal to e to the 3x. So that shouldn't be too hard to see. The antiderivative of 3 is 3x, and we know this because the derivative of 3x is just 3. So that all works out. We have our mu of x. Now let's do step number 2, and let's multiply through our equation by this integrating factor. So by the way, this is called the, and maybe you'll see why after we learned about it, is called the integrating factor. So if we multiply through, we have y prime times e to the 3x plus 3y times e to the 3x equals x squared e to the 3x. Okay, now we have, remember that this whole expression is really going to be the same as y times e to the 3x, and then the derivative, so we can write prime like this, equals, this side is unchanged because all we're doing is this reverse product rule step. And now we can take the antiderivative of both sides, so we have y times e to the 3x equals the antiderivative of x squared. And let's make this more rigorous. It's the antiderivative from 0 to x of, we can use t. So we can say t squared e to the 3t dt. So we're using this because really, if we can't use x because x is still going to be a variable that we're changing, so we want to use t in our integral and then x as the bound. And then this is plus c. So now let's evaluate this. We can evaluate it over here. This one's kind of nice. We have the of t squared e to the 3t. This is sort of the perfect one to use integration by parts. So integration by parts, the rule of integration by parts is that the antiderivative of u dv is equal to uv minus the antiderivative of v du. So that might seem kind of complicated. Basically, we have two functions here, and we're going to pick one to be u, and we're going to pick one to be dv. And so I'm going to say the t squared. So we'll say u is equal to t squared, and dv. And also, wait, I should correct myself, because technically we are having e to the 3t dt. This whole thing is dv. So dv is equal to e to the 3t dt. So the dt is still technically part of the integral, and that's why we have dv over here. Like, we don't have u, then something, then our d term. We just have u dv, so this is going to be equal to this whole thing right here. That covers all our bases. And so now we have two other things we need to find. We need to find du, and we need to find v. So the way we find du is, this is kind of funny. It's a weird way of writing it, but basically what we want to do is we need to take the derivative with respect to t of both sides. And now I'll write it in a separate line. So we can say du over dt is equal to the derivative with respect to t of t squared. And so we could say that du over dt is equal to this is just 2t, right? The derivative of t squared is 2t. Now we just bring the dt over here, so we have du is equal, wow, that was a terrible u. Du is equal to 2t dt. So now we have du in terms of t. Then we want to find v, and so to find v, we actually have to take the integral of both sides. So we have the integral. Okay, let's do it better. So we have integral of dv is equal to the integral of 3t dt, or 3e to the 3t dt. And so this is just v. And then now this expression, well, we kind of know how to do these. It's going to be 1 over 3 e to the 3t. So now we can we can say that our, let's see, we have u and we have v. So now let's calculate this. So u is t squared, v is this. So this first term is t squared times 1/3. We can do this. We can say 1/3 times t squared times e to the 3t minus the antiderivative of v, which is this 1/3 e to the 3t, and then du, which is this one, times 2t dt. And now we kind of have to do the same thing over again, except this time it will be the end of it. So just bear with me here. We can make some more space, and this is important to know how to do. You need to be comfortable with evaluating these integrals. They're not like, it's a little bit of busy work. So this is sort of our work here. So now we need to evaluate a new one, which is, we need to evaluate this one. So we have 1/3 e to the 3t times 2t dt. And let me write that differently. So we can say it's actually 2t times, so we keep it in the same order as before. And I'm going to pick this to be u, and let's use green again. So this is going to be u, this is going to be dv. So we have u equals 2t, and just to skip a step, we know that du is equal to 2 dt. It's the derivative of this guy. And then dv is 1/3 e to the 3t dt. Taking the integral of this expression, we have v is 1/9, so we have another 1/3 coming down, e to the 3t. And so now, now we know that this is equal to our u times v. So we have, let's just say 2/9 t times e to the 3t, and then minus the derivative of v times du. So we have 1/9 e to the 3t, and then times 2 dt. And now that was the last time we had to do integration by parts, because and also remember, this term here is going to be stuck onto the end of our sort of running answer. And actually, let's do that right now. So I'll grab this and move it down here, and so we can say it's not. We can replace this, and so remember, we're subtracting. Actually, let's just replace this with this expression in parentheses. And so now this integral right here is the only thing we have is an e term, like an expression term, which that's kind of easy to find. So this is the same as, we can pull our constants out, and then that's the same as, we can remember another 1/3 comes down, so we have 2/27 e to the 3t. So since this is the same, we can sort of just replace it in here like that. It's kind of messy. And now to evaluate the whole thing, and also we can get rid of this guy. And there's a shortcut for this, by the way, but I'm doing it the long way so we can see better. So now to write down all our terms, we have this integral right here is, you can write the integral of 0 from 0 to x of, we could say, actually no, that's not true. We have to evaluate it still, but let's just say the integral of t squared e to the 3t dt is equal to, we have this 1/3 t squared e to the 3t, and then this is a minus, so we have minus 2/9 t e to the 3t, and then plus 2 over 27. It's plus because we have a minus here, and also minus here, e to the 3t. So let's just take out, factor out e to the 3t here. So we have 1 over third, or 1/3, wow, 1 over third, 1/3 t squared minus 2/9 t plus 2 over 27. Okay, so that's a much nicer form now. And now we need to evaluate it at the bounds of the integral to find the answer in terms of x. So we could say this, evaluated at 0 and at x. Well, at actually, we can just evaluate at x. So at 0, if we evaluate at 0, basically what's going to happen is this term equals 1, and then these terms equal 0 because t is 0, and then we have this 2 over 27. But the thing is, we're adding a random constant at the end anyway, so this is just going to be absorbed into that constant, sort of. Like, we're going to have some big long expression plus 2 over 27 or minus 2 over 27, and then we're going to have plus c after that. So that we're going to just ignore that 2 over 27 for now and just evaluate at x. So this is just 3 times e to the x of 1/3 x squared minus 2/9 x plus 2 over 20. Actually, yeah, I guess we have to keep the 2 over 27 there. So we have y times e to the 3x is equal to e to the 3x times 1/3 x squared minus 2/9 x plus 2 over 27, and then plus c. Now we have to divide both sides by e to the 3x. We want y to be by itself, right? So to divide both sides, we have y equals, so these are going to cancel out, and then of course this one still needs to be divided. So to do that, we have 1/3 x squared minus 2/9 x plus 2/27, and then plus c divided by whatever, e to the 3x. And I'm going to write this in a nicer form. I'm just going to e to the minus 3x. So remember, if we make our exponent negative, it's corresponding to saying 1 over that exponent. Yeah, so now we have technically finished the problem. This would be an acceptable answer in differential equations. So we can kind of remove all this stuff, get rid of all that, and put this over here. So the final answer, y equals, and can we make this nicer? Probably. Let's see. Are there any shortcuts we could do? Nah, we don't need to. We don't need to get distracted by all that. So we could say y equals 1/3 x squared minus 2/9 x plus 2/27, and then plus c times e to the negative 3x. So that's pretty cool. And so we can use this to sort of think about how our slope field would look. So let's think about how like things tend to go when x goes to infinity or negative infinity. So let's think about when x is going to infinity. So over here, right, way over there, that's going to be infinity. Way over there, that's going to be negative infinity. So at infinity, let's see. So the x squared term, right, this is going to go to infinity as x goes to infinity. This is going to negative infinity, but it's not x squared, so it's going to be, it's funny to say, but it's not going to be as powerful as the x squared term. This is going to stay the same, and then c to the e to the power of negative 3x, well, that's just going to go to 0, because if we have negative infinity in the exponent, that's 0, and so we know that as x goes to infinity, basically y is also going to go to infinity. Now let's think about negative infinity. So let's say what happens is x goes to negative infinity. Well, this term is going to be x squared, something negative that's squared is positive, that's going to infinity. And then remember, these terms don't really matter because they get overpowered by the x squared term. This exponential term, however, x is negative now, so that's going to say, like, if we think about it, e to the 3 times infinity. So that's the same as e to the infinity, and that's also infinity. So this is going to positive infinity, and so that's saying that basically as x goes to negative infinity, y is also going to go to positive infinity. So our at the very ends of our graph, the all of our solutions are going to be going up. And then if and this is for any x, so even down, like if something is down here, right, eventually it's going to find its way up. It's going to find its way to either infinity or here. So yeah, it's pretty cool. I like it. I think it's super cool to go and graph different values of c. So what you can do is go into like Desmos, and actually here I'll do it right now. Go to Desmos.com, start graphing, and we could say 1/3 x squared minus 2/9 x plus 2/27, and then plus c times e to the negative 3x. And so let's graph c, and we can say c is 1. We can go -5, -4, -3, -2, -1, and then 0, 1, 2, 3, 4, 5. Okay, so let's just get a little screenshot of this. So here's what the graph looked like at the end. I can put it over here. Kind of overwrite some of it, but it's okay. So there's one thing I actually forgot, and this is why it's good to go and graph, is that what happens when c is negative. So I said that this e term, this will go to infinity when x goes to negative infinity, right? So x is going to negative infinity. We have negative 3 times x. That's sort of like that's negative infinity, which is positive infinity. And then this is all multiplied by the c term. So if c is negative, right? So these terms are negative. Now this graph is going to go to negative infinity because that's sort of being inverted. All that hard work is being inverted. And then for the ones where c is positive, now it's going to go to positive infinity. And then as the graph goes the other way, we noted that the x squared term, this is going to infinity. These two don't really matter. And then this e term, that's actually going to 0. So that's sort of why all of the here's another way to think about it. The only thing that's separating these red lines is the c term. So for all of them, this x term, and this x term, they're all the same, right? Because this is the same graph, just with different levels of c. So here, like let's think about in this range, they're all pretty separated, right? Because e to the negative 3x, that's still, like if we think about e to the negative 3x is kind of looking like this, right? That's still going to have some influence in how this system is going. But as x gets bigger and bigger and bigger, then so we have e to the negative 3x, right? This is going to get smaller and smaller and smaller and smaller and smaller. And so the difference in c, it's not going to matter as much because it's being multiplied by a smaller and smaller number. So that's why up here, all the lines seem to converge onto one line. And it's true that as we get super far this way, any value of c is going to converge onto almost basically a single line, because the influence of c in the equation is going to be very, very, very small, because this exponential term dies off at a, wait for it, exponential rate. So there you go. That is integrating factor. We took a differential equation, which was y prime plus 3y equals t squared, right? And we figured out this is a graph of some of these solutions. We figured out sort of a general form of the solution, which was some terms that correspond to x, and then plus this c e to the negative 3x term, and that is for different starting locations. You can kind of think about it, if you started here, you'd follow this line. Well, if you started down here, you'd follow this line. Or if you started down here, you'd follow this line. Right? So that's how you can think about all these different lines. And so maybe if you're up here, your line looks like this. Right? Or if you're down here, maybe it looks like this. I don't know. It would be different. But you'd have a line from wherever you start from. So that is the integrating factor ultimate review. If you have a differential equations test coming up, I wish you good luck. Hopefully, if you have a differential equations test, then you are more than familiar with integrating factor. But maybe this is a good refresher on the intuition behind it and sort of how and why it works. So integrating factor is the name of the method. And yes, so good luck. Hope this was interesting, and goodbye.